Hello, I'm SeungWon Seo. Today I will be presenting the paper title Hierarchically Structured Open Vocabulary Endorsing Synthesis with Pre-trained Large Language Model, which was published at AAAI 2025. In this presentation, I will cover the following topics. First, background and the challenges in endorsing synthesis. Second, the problem formulation. And third, the proposed method, which include an LLM-generated hierarchical structure, a hierarchical aware network, and divide and conquer optimization. Next, experimental result and comparison with other approaches. And finally, conclusion and potential direction for future work. Endorsing synthesis is crucial for applications such as interior design, VR, AR, and other related fields because it generates realistic and functional 3D layout. However, creating such scene is challenging due to the need to balance aesthetic appeal, physical plausibility, and functional object arrangement while accurately capturing the complex spatial relationship among objects. Traditionally, approach to scene synthesis relied on rule-based method with handcrafted constraints which were limited in their generalization. Later, data-driven techniques were introduced, though they still struggled with modeling complex scenes effectively. Recently, deep learning models such as autoregressive model, GAN, and diffusion models have improved scene generation. In addition, some LLM-assisted approaches generate text-based scene description, but these methods face limitation in spatial reasoning. Existing intermediate representations also have their shortcomings. Numerical layout that directly predict bounding boxes often result in overlapping objects or placement outside the designated boundaries due to LLM's difficulty in precise spatial reasoning. On the other hand, dense scene graph with detailed pairwise relationships can become self-contradictory when scaled to multiple objects. This motivates the need for a hierarchical approach that uses a coarse-to-fine strategy, which avoids excessive constraints and allows for functional grouping and robust global organization. In this work, the problem is defined as follows. Given a natural language description, for example, a small bedroom for young student, the goal is to generate a realistic and physically plausible 3D indoor scene. The scene is represented as a set of objects, where each object is defined by a selected 3D model and its spatial layout, including its position, orientation, and scale. To simplify the synthesis process, the author proposed a hierarchical scene representation. The scene is divided into three levels. The root node represents the overall scene, including global parameters such as room size and a global description. The internal node represents functional area within the scene such as sitting or workspace area, acting as anchor for grouping related objects. Additionally, we can capture local spatial arrangement based on functionality by specifying a text description, the size attributes, as well as center position and an orientation. This ensures that each functional area has clearly defined bounds, a descriptive label, and a consistent orientation. The leaf node represents individual objects with specific attributes such as category, size, and orientation. Concretely, each leaf node may include a text description, the category label, the corresponding 3D model, as well as the size, center position, and orientation of the oriented bounding box for the object. Hierarchical scene representation help break down the scene synthesis task into smaller, more manageable steps, making it easier to handle complexity. Additionally, by grouping objects according to their functional role, this hierarchical naturally improves physical plausibility and overall organization within the scene. The first component of the proposed method is the LLM-generated hierarchical structure. A carefully constructed prompt is fed into the LLM, which includes the role definition, preferred data format, constraint, and an example scene. The LLM outputs a three-level hierarchy consisting of a root node for the entire scene, an internal node for functional area, and leaf node for individual object. Additionally, the output included sparse textual relation, such as bed in front of the nightstand. This approach avoids overly dense or purely numerical. description, thus reducing the risk of contradictory placement. The second component is the hierarchy-aware graph neural network, which refines the spatial detail. In this network, nodes represent object or functional area and edge capture pairwise spatial relationship. Node feature combine the clip text embedding of object description with size embeddings, while edge feature incorporate the textual relationship embedding and initial relative placement data. The network uses an encoder-decoder structure with multiple rounds of message passing, where edge distributions are parameterized as Gaussian, and the decoder sample fine-grained relative placement such as position and orientation. The training loss include a KL divergence term and error loss for position and cross-entropy loss for angle and alignment. The third component is divide and conquer optimization. This process is divided into two stages. For local optimization, within each functional area, the author rearranges objects around an anchor object. This process minimizes overlap and ensures that objects stay within their designated boundaries. Then, for global optimization, these functional areas are positioned throughout the entire scene, making sure they are appropriately placed, such as near wall, and that they don't overlap one another. Finally, the optimized layout is used to retrieve suitable 3D object model from database, like observers or 3D front using clip-based similarity measures, and the objects are scaled and placed accordingly. In the experiment, the 3D front dataset is utilized, which includes various indoor scenes like bedroom and living room. During preprocessing, scenes with irregular or non-rectangular floor were filtered out to ensure realistic layout. The training combined samples from different room types, and the models were trained on NVIDIA 4090 with a training time of around 8 hours. The LLM generates the hierarchical structure, while the hierarchy-aware network and optimization modules are trained separately. Several metrics were used to evaluate the generated scene. First, for physical plausibility, they check how much the object bounding boxes overlap and whether any objects appear outside their designated boundaries, which they refer to as out of bounds. Next, to assess relative spatial consistency, they use statistical measures like KL divergence to compare the distribution of relative placement in the generated scene with those in real scene. Finally, for semantic alignment, they measure how well the text-based spatial relationships generated by the LLM, like saying in front of, match the actual spatial arrangement. This is quantified using metrics such as the relation matching ratio and the object presence ratio. Quantitative results indicate that the proposed method outperformed baseline. The method achieves the lowest value in both overlap and OB, demonstrating high physical plausibility. KL divergence score are the lowest, suggesting that the predicted relative placement closely match those in real scene. Additionally, semantic alignment metrics show that the generated scenes are highly consistent with the LLM's text description. Visual comparison reveals the strengths and weaknesses of different methods. Deep learning-based methods such as ARTIST and diffusing can generate reasonable layout but often suffer from object overlaps and out-of-bounds placement. LLM-based methods like Layout GPT and Holodeck generate layouts that align with text description, yet may encounter numerical inaccuracy. The proposed method consistently generates scenes that are both physically plausible and semantically aligned with the input text. Ablation studies were conducted to validate the contribution of key components. Removing the hierarchical-aware network force relies solely on textual relationships, which degrade the ability to fine-tune placement. Removing the divide and conquer optimization leads to poor physical plausibility, as both local and global optimizations are critical. This experiment demonstrates that both components significantly contribute to the overall performance of the method. The method's capability in open vocabulary scene synthesis is also evaluated. The approach generates scenes from text description that are not limited into limited to a fixed set of object categories. Challenges include handling diverse and unseen object categories while maintaining physical plausibility and semantic alignment. By leveraging the hierarchical scene structure generated by the LLM and refining spatial detail with the hierarchy-aware network, the method successfully synthesized plausible scene in new domains. The experiments show that this method can robustly synthesize scene even in new domains like museum or arcade. Essentially, it opens up existing opportunity for more creative, user-driven, and interactive scene design. The paper proposed an integrated pipeline that combines an LLM-generated hierarchical structure, a hierarchy-aware network for spatial inference, and divide and conquer optimization to generate realistic 3D indoor scene. The method achieves superior physical plausibility and semantic alignment compared to existing approach, and it works robustly across various scene types, even in open vocabulary setting where object categories are not fixed. However, a limitation is that the current assumptions, such as assuming rectangular floor, might restrict its ability to handle more complex layout. Thank you for listening.